Hello, everybody, and welcome to the Protocol Town Hall. We will get started soon here. Just take off this banner before I forget. And thank you for tuning in. We took a break last week since we were up at Edge Esmeralda for our Protocol Worlds 3/retreat for the summer. It's good to get everybody there. And today we're kicking off our summer guest talk series again. And the focus moving forward will be a combination of both technology, engineering, and pedagogical stuff, since we're focusing on education this year. And today we have with us Vikram Sakar, who I'll bring on the stage soon. And Vikram is a writer and engineer who talks about a lot of stuff. He's got over 15 years of experience working in the industry in both the US and India. He has a PhD from Texas A&M University, and he's worked at the forefront of radio frequency engineering technology in several major semiconductor companies. He writes about this stuff on his newsletter called Vic's Newsletter on Substack. I highly recommend it. I've been reading it lately, and it's been a real big learning curve for me, with weekly technical deep dives and some more longer form stuff, as well as actionable advice for students, which we're kind of catering to this summer. So I'll bring Vikram on, and we might have to sort out some stuff with slides, but welcome to the show, Vikram.
Hey, Temba. Thanks for having me on.
Do you have slides?
Yeah, I do actually.
There's like a little present button at the bottom you should be able to see, and you can add your slides to it.
Okay. Google Slides.
This is good. When we were up at Protocol Worlds at Edge Esmeralda last week, we had a ton of people that wanted to join, and it was more interest than we had in the past. And we kept trying to figure out why do people want to join? And it's because I had put a bunch of sessions in the mornings that were closed, and they said closed on the calendar, and people were like, oh, now I really want to come. And it's kind of this suspense building. Okay, I see the slides there. Let's see. Add to stage. Okay.
All right. Hopefully we can see it now.
Yeah, it looks good. There's a bit of background noise coming from your end, but.
Oh, okay. Let me know if that goes away.
Yeah. I think that's a bit better.
Okay.
All right, I'll leave you to it.
Okay, thanks, Timber. That was a good introduction. You pretty much covered all I wanted to say about myself. Thank you, everyone, for being here and attending my talk on protocols in electronic design. I have a rather larger umbrella of stuff I want to talk about because as I was thinking about protocols in electronic design, one thing led to another. So hope I have a few interesting stories that I can tell you about this today.
Hey, Vikram, sorry, one sec. Your audio's it's good for a second, and then it's kind of knocking out for a couple seconds.
Oh, okay. Let me try.
Yeah.
How is that?
That I think is much better. How about we go with
Okay.
that?
Okay. Then I'll just go with the laptop audio. That's just fine.
Okay.
All right. Awesome. Thanks for being here. Let's get into this. I have to put this disclaimer because I have to make it clear that I'm talking based on my own opinions and they don't reflect the views of my employer as part of the ethical protocol I'll mention later, and that this is for information only and not advice by any means. So after that is done, so my name is Vikram Shekhar, and I'm on LinkedIn and X if you want to follow me on there. Primarily, I'm an engineer by profession, maybe a scientist at heart. I've been doing RF circuits professionally 15 years, and if you count school, it's nearly 20 years now. I'm currently an engineer at Qualcomm, where I work on RF front-end devices. And front-end meaning anything that's closer to the antenna on any communication system, be it your phone or whatever else. I write a Substack publication on vicsnewsletter.com. I cover twice a week posts on semiconductors and RF, analog power photonics, and anything else that might come along my way. And this so dynamic and changing that my interests never seem to hold to one particular topic. So I just let it go and follow my interest. And so far, I hope people reading it are enjoying the whole journey as well. Okay. All right. So I have to get my notes up here. Sorry, just 1 second. Okay. Yeah. Now, what are protocols in electronic design specifically? And the way I look at this is that it's a bunch of operating principles that underlie, everything that we do in electronics, right? It could be explicit rules, it could be implicit rules, it could be technical, it could be how we operate and talk to each other, what the culture of a workplace is that designs electronics, and how the politics of it all works out. So there's a whole gamut of topics we could talk about just about protocols in electronic design. Now, when you say something like standard, is kind of, you can think of a USB is a protocol, right? How USB devices exchange information could be a protocol. But then if you talk about intellectual property, it's interesting because now we have to somehow have rules about where and who owns what, right? Even if that's something as abstract as an idea, and when and how it can be used. How do we share intellectual property? And violations of these things are normally billion-dollar affairs, as we see in lawsuits and things like that. And then there are codes of conduct, how we should behave with each other, and how personal and business relationships work. And then we have compliance and regulation, which is there are specific rules that electronic devices have to meet in order to be functioning properly. And then there's ultimately something called trade policy, right? So who can sell to whom? How do we export stuff to the other countries? How do we deal with mergers and acquisitions? How do two big companies merge? And what are the antitrust, anti-competitive laws to promote free and fair competition? We'll cover a large portion of these ideas, but not all. This is very, very wide. So essentially, when I look at the categories of protocols in electronic design, you could put it in these ways. Standardization, basically the USB example. How do we establish common baselines for everybody? The other one is communication. Sorry, I have to go to the next slide here. The communication, right? How do devices talk to each other? And validation is how do we make sure that the electronics is either going to work or is working as we intended? What are the protocols for the methodology, which is what are the best design practices? How do we make sure we design things in the right way to get it done properly in a reasonable amount of time? And documentation. This is very important because chip design and electronics today is so complicated that it is never usually done by one person or even a small team of people. You've got hundreds of people working globally who need to share information effectively with each other. And then cultural boundaries. How do we work together? What are the right ways to do this? And then ethical protocols, how to do this with integrity. And lastly, the political protocols of the geopolitics in electronics. Now, I like this particular idea, and this is relatively new to me because I am new to the field of protocol studies, and this has really got my attention because this is one of the first few articles I read on the protocolized Substack, and I was like, this is great. I mean, this applies to so many things in electronic design that it stuck with me ever since. The idea of a trade-off is well known to engineers. Like from the very get-go, the moment we are taught how the physics works, we are immediately taught how there's always something in A versus B, and then they're contradicting, and then you got to pick something in the middle and call it a day, and that's called a trade-off. Now, I like the concept of attention because it's it's a superset, I would like to think, of what a trade-off is. where a trade-off is, a definitive stance on maybe a few contradicting goals. This tension is always changing, might not always exist. It has social components to it. It has conflicts between people, entities, organizations, and may always be changing. And so the concept that there is no solution to the problem, it's only a management of the problem, is an interesting concept to me. So, and this theme will keep recurring in the talk, and I wanted to put this up front so that we can revisit this idea as we go through the rest of this. The other idea I'll keep revisiting is another one I picked up through the protocolized Substack, and that's the efficiency thoroughness trade-off. Because it's a slight deviation from the tension idea, I figured this fits perfectly into what we do in electronic design as well. I'm not exactly sure how many people in the audience have seen this, but I'll just go through this. On the x-axis, there's the efficiency. So one could get too efficient and not thorough enough, which means you try to get it done quickly maybe, and then don't look through everything. And there you're going to fail that way. Or you get too thorough and not efficient enough, which means you don't deliver your product on time. And now you have a thoroughness failure. So between these two, there is this efficiency thoroughness trade-off frontier, the Eto frontier. And there's always a tension on which way one should go. And there is an entire, the frontier can move. And there are occasions where this has happened, and I'll give you an example of that. But I want to bring a simple example I wanted to mention about the tension idea when looking at electronics, is that if you look at the classic trade-off in, let's say, chips where you have power versus performance, you can always get more performance from chips by burning more power, right? So you burn more current, you get more performance out of the chips, which is not a problem. Sometimes the application demands it. So if you are designing chips for a data center to do AI inference or AI training, then you need to have a lot of processing power, and you don't mind spending the performance. Okay, that seems like a simple enough trade-off to do. You just go for performance, not power. But then you run into other problems, right? Now, how do you cool this problem? How do you cool the system? Because now that you're burning so much power, there's going to be a lot of heat. And now, who's going to provide the cooling solutions? Because NVIDIA, for example, is rumored to have one key supplier who provides for the data center cooling solutions. So now you have a supply chain issue. Then you have power utilization issue, because data centers now suck up megawatts of power. And there's even talk of hooking up nuclear plants to power data centers, which to me is very fascinating, because you're using something very tiny. Nuclear power comes from a tiny source to power something else that is very tiny, which is a transistor, through an entire chain of really large systems. Like fabs are really big, and nuclear power plants are really big. And then, of course, there's talk of Microsoft wanting to restart a 3 Mile Island for nuclear power reasons, and it was shut down due to climate impact, at least suspected climate impacts many years ago. So something as simple as a power performance trade-off has now gone all the way up to climate, right? You see how this idea of a tension, whether it's power or performance, has now exploded into how trade-off has exploded into a tension now. So there's so many things to look at when just discussing simple trade-offs like that. Now, so when we talk about standardization protocols, this is very important, because there are established metrics that are like interfaces between standardization protocols. Like the USB was, the device A has to send out these many packets. It has to have this in the header. This has to be received. This has to be read. There's an order to go through. So this defines the interface between them. Now, these standardization protocols are very important in pretty much everything that we do. Like units of measurement is a fundamental one. It's a very hard protocol. And the violation of this, and I'll get to this later, has serious consequences. And bad stuff has happened when measurement units have been violated. And then you've got mechanical stuff, simple stuff like, you've got to have a USB-A versus USB-C connector. But turns out we still have both of them going on. We would maybe just want USB-C, but then there was lightning and there's no lightning. Then you've got all these standards about what voltages should be, what current should be, what impedance should be. Spectrum handling from the FCC tells you what radio bands you can communicate in, and thermal conditions, what ranges of temperature it needs to operate. Like space has different stuff, requirements. Industrial electronics has different requirements, and then you have different protocols for quality, reliability. Automotive qualification of electronics is quite different from space qualification of electronics, and they all have their independent standards that must be met. So what ends up happening is, ideally, the way this works is that you have one governing body that tells you, oh, this is the way, this is the protocol, this is how you should do it. Turns out that never happens. And so this classic XKCD comic always comes to mind, where you have so many competing standards, and then, well, now you have one more, and doesn't solve anything. But that's how it is, right? So I'll tell you a few interesting things about some standardization protocols out there, and maybe some ways in which they fell apart as well. Okay, so the NIST is the shining beacon in human consistency, because they are responsible for defining a lot of important standards that we use today, especially in terms of measurement. And the way they do these things are fascinating. So notably, what they define is the notion of a second. So what they actually have is this gigantic machine on the left you see here, called the cesium clock. This is called an atomic fountain clock. And the way it works is, right from the bottom of this cylinder, there's a cesium atom that's like shot through this cylinder, and it goes all the way up to the top, and it falls back down. And when it falls back down, it is interrogated with microwave radiation, and the number of oscillations of the cesium atom is measured, and it turns out it's a very precise number wherever you take it in the universe. Like, you could measure a cesium atom at the far ends of the universe, and it's always going to give you these many oscillations. It's in a frequency sense, it's like 9.19 gigahertz. So the number of times it takes to do this is 1 second, right? The number of oscillations. That's a very precise definition. And this particular clock is so accurate that it loses maybe 1 second in every 100 million years. And that's and there is a reason we need this kind of accuracy, because GPS today will not work unless we have this kind of time accuracy. And the reason is, if you think about it, distance is basically speed times time. Right? Yeah. And then the speed of light is really, really high. And so your time measurement intervals need to be really, really low if you have to get the distance measurements right. So that's why you need to have really high precision timing equipment and time synchronization between various satellites and your phones and everything to make sure that you get high level of GPS accuracy. Now, if you want to, I highly recommend reading a book by Dava Sobel called Longitude. It goes through this entire history of timekeeping and how people needed accurate clocks to keep direction at sea. It's a fascinating read. It's a really tiny book, my kind of book. But otherwise, NIST also has some interesting stuff, because they have this really long tunnel in which they measure tape measures. They even have a standard ignition test for cigarettes. But then this is even going. They don't stop here, obviously, because the future of timekeeping involves something called the optical lattice clock. And the purpose of this clock is to trap, I think, strontium atoms in a web of light. So basically, lasers hold a strontium atom in place, and they measure the strontium atom and its properties. I'm guessing it's still oscillations, but the point is that this is even more accurate than the previous clock. This loses only 1 second every 30 billion years, which is twice the age of our universe. This has not yet become the gold standard of time. It's still the fountain clock, but this is where we are going. So these kinds of things, time is a hard protocol. Okay? When somebody says 1 second, there's a very definite meaning to what 1 second is. This is not open to negotiation here. And there's also a measurement protocol to what 1 second means, because it's measured within the microwave Ramsey interrogation of a cesium atom in that cylinder. And once we know what a second is, we share that. It's a shared reference protocol between different systems, navigation, communications, and even high frequency trading requires that kind of synchronization. The other kind of standard that comes across in electronics is, this was a while ago, but the transistor logic, TTL, because the early days were all bipolar devices, and people needed a way to make digital circuits with them, and you have to say, okay, what voltage is a 0 and what voltage is a 1? Like, it can't be arbitrary, right? Like, how does the system decode what is a 0 and a 1? So this was a boundary protocol that separated the two states. And the way this came about is because there are definite ways in which a transistor at that point, a bipolar junction transistor, which we don't use much anymore. We use CMOS, a complementary metal oxide devices. That's what everything is made of these days. But the bipolar devices in the earlier days required a certain amount of voltage to make sure they're turned on and a certain amount to turn it off. So this evolved as a function of that. But this is an example of a well-used boundary protocol in electronics. And this is another interesting story. So, like, as we're going down this path, as you can see, like, there are different reasons we establish these things the way they are. But this is an interesting one because it's very loosely defined. The way 50 ohm is an important number in RF electronics. Anybody you talk to is always going to keep referring to this number, and if you're new to this area, you're going to wonder why 50? Why not 100? 100 is a much rounder number. Why would anyone talk about 50 all the time? So it turns out that this is a special chart that RF engineers always tend to use. And this is actually even hard to come by. If you look at all the Python plotting algorithms and all the plotting tools, there are very few plotting functions that actually plot this. And I think Plotly .js, I think, finally implemented the Smith chart after many years, which was interesting. But most tools don't plot this thing because it's so specific. Now, this is a tool used pretty much entirely in RF to match circuits, design circuits, and it's used for a whole lot of stuff. Everybody puts this chart up. But the center of it corresponds to 50 ohm, usually. The center of it is normalized to some value, but it's usually 50 ohms. And that's what, that's how important this is. The chart that's used most all over RF engineering is centered around 50 ohms. And the reason this is required is we need something like a 50 ohm reference and any reference value. And that the reason is because we want to build communication systems like we build Legos. Basically, we put blocks together, right? So if you look at this picture on the left side, you have the antenna, and you have some filtering and some switching, and then you have two parallel paths. One path is for the transmitter, down, and the up path is the receiver. Now, each of these blocks have a different function. Like the triangles amplify, the squares with the wiggles on them, they filter signals. The one with the X on it, it changes the frequencies from a high frequency to low. Anyway, they all have their functions in a signals processing system, in a communication system. The nice thing about having 50 ohms is if everybody designed to a 50 ohm system, you could just Lego block them all together and they work perfectly, which is what everybody wants. Nobody wants things that are like, when you put them together and they don't work, right? That's terrible. So it served that having a common value of reference, a protocol to design to, means that somebody could design the amplifier, some other company could design the filter, and we could just put them together. But the question is, where did this actually come from? Because this dates back to early military radios, and it came from basically coaxial cables. Now, coaxial cables are pretty simple structures, and we still use them. They have a center conductor here with a radius of A. They have an outer conductor with a radius of B. between the two, there's like, it could be air or it could be material like Teflon or some polymer. That's pretty much it. Now, depending on how you choose A and B and the Teflon in between, a coaxial line has a very specific property, and that's called the characteristic impedance of the coaxial line. Now, the coaxial line is so important because it basically tells you what is the resistance you will see if you measure this end of the line, while the other end is infinitely long, right? If you have an infinitely long line and you measure the coaxial line, the impedance of the line, this is what you will measure. So the military wanted a standard value for Z0, which is coaxial characteristic impedance, because they wanted to Lego block all their systems and it's going to work out just fine. Now this comes at a cost, right? Because the trade-off here is, if you find out how much signal loss the coaxial cable has for various characteristic impedances, it has its lowest signal loss at 77 ohms. However, if you want to you have the highest power handling, which means how high of a signal you can put through this before your cable actually melts, kind of thing. The ideal value for that was 30 ohms, right? So there you have these differing, completely opposite ends, because because it depends on the application. Sometimes you want signal loss, sometimes you have power handling. So what everybody did was just say, like, forget about this, just take the geometric mean, call it the Goldilocks zone, which if you take it for these two numbers as 48 ohms, you wing it some more, round it off to 50 and say everybody design it to 50 and move on with it, right? So that's how 50 ohms actually came to be. And it was good. And the reason why this worked out was because if you have a cable much higher than like 80 ohms or 100 ohms, they're difficult to manufacture, because the signal may short out with in one case the signal shorts out, in the other case the cable gets too bulky. So if it's below 20 ohms, it's annoying. If it's above 100 ohms, it's annoying. So 50 ohms was great. It was mediocrity at its best. It could be used for a lot of stuff. Power handling was not terrible. Signal loss was not terrible. And this was great because everybody now jumped on board. All the test equipment manufacturers, like at that time it was HP, and then whoever made radio equipment at that time jumped on board with this. They were happy because they had to cater to the military. And so this entire industry was built about this humble coaxial cable and the need to have a balance between power handling and signal loss. Again, this is a soft protocol. Like, people just like they just wing it and come up with this 50 ohm number. But then it turns out that 50 ohm isn't great for everything. Like, if you pick up one of those blocks and you say RF amplifiers, like, amplifiers don't really like 50 ohms. They don't want an output load for a transmitter or an input load for a receiver to be 50 ohms. They want something else. They want something that they want to see if you want to have the best power and efficiency for a transmitter amp. So if you want the transmitter to put out a lot of power, it needs a different load. And if you want it to be highly efficient means how much RF power it puts out for the amount of battery power you give it, right? Then you need a different load. So, and then if you're a receiver, you want the receiver amplifier to be very low noise, because the signal received is already weak. You don't want your amplifier adding further noise and messing up your signal. So to get the best noise performance for the receiver amplifier, you need another load that is not 50 ohms. So now how do we Lego block stuff, right? So this is the tensions that we deal with all the time, because you trade off Lego blocking for performance. And at some point, everybody has to get together and come to an agreement about what is okay to do regarding this. Okay, so this is another example of, now I would say this is a hard protocol, because the Federal Communications Commission has fixed standards. So they have the radio spectrum in the United States, and this is a map of it. And each color here shows like a different application for which the spectrum is allocated. Now, spectrum is a very, very valuable resource because it's finite. Like between 1 gigahertz and 10 gigahertz, there's only so many gigahertz in between. You can't invent gigahertz, you can't make gigahertz. So this is actually a very valuable natural resource in a sense. And it is auctioned, each spectrum block is auctioned often for billions of dollars. And the reason that such hard protocols exist here is that nobody wants another person to encroach on their spectrum, especially when they've paid such heavy amounts of money for it. So that's there are very specific protocols for neighboring interference. So a neighboring communication system operating in a band next to you cannot interfere with your own communications. So there are limits set for how much that can happen. And violating these limits has some serious implications, as we'll see next. So an example I have that we can talk about is what is now an evolving technology called direct-to-cellular technology. So what this is we put cell phone towers all around the cities, and in urban populations, we put quite a lot of them to have good coverage. And as you go outside the city, you drop the number of cell phone towers, you lose signal, your connectivity is sparse. So the idea is, why don't we put cell towers in space? So once you put them in space, you could beam them. They could act just like cell towers on Earth, and you could beam it anywhere you want and provide coverage even to the remotest areas without having to deal with any of the local geopolitics of the land and the ability to build there or any such thing. So it's a great idea. So the idea for this is that it should provide supplemental coverage from space, only supplemental. This is not going to replace terrestrial towers, because ground-based communications are always going to be faster and more bandwidth. This is only for cases when you don't have it. Like if you want to put a industrial sensor that want to communicate with aboard an oil rig in the middle of the ocean, this is a good use case for supplemental coverage from space. Speed is not the issue here. We just want to make sure it's alive. But the one requirement that this technology has is that it must not interfere with terrestrial networks. Okay, this is just supplemental coverage. So there are strict radio emission limits set by the FCC, saying stay in your lane, do not mess up what we have. So what ended up happening very recently, I think this drama just kind of died down a couple of months ago, is Starlink's violation of this protocol and saga that ensued. So FCC's protocol is that the out-of-band emission, that is how much you can violate and get into the next person's lane in the spectrum, is a number that is, say, minus 120. Let's not worry about the watts. This is about radiated power in an area per megahertz of bandwidth, that kind of unit. But the number minus 120 should do. But Starlink says it's too restrictive for them, and they want the waiver to be at a minus 110.6. Now, this is in decibels, so this is a logarithmic scale. So 10 decibels is 10 times, right? So you're almost asking for a waiver for having 10 times more emissions in the neighbor's lane, and people have a problem with that. So the competitor, which is AST Space Mobile, and their partners, which is AT&T Verizon, said that this is unacceptable because this means that their network is going to have 18% lower network throughput, because Starlink is partnered with T-Mobile, and AST and Space Mobile is working with AT&T and Verizon, as I last looked it up. So this is a big problem, and especially the European telecom companies said that this is a big problem for us because we are more geographically constrained, and we don't want emissions to go very far. We have very strict limits, and we will sue the FCC if this waiver is granted. We don't want 10 times more emissions. And so this became a big drama, like Starlink calls AST a meme stock and spreading misinformation, all that stuff. Anyway, I wrote a whole post on this thing, and it was very interesting, but then it hadn't concluded at the time I wrote the post. So I recently looked it up, and it looked like FCC did grant the waiver to Starlink at the end of the day. And the emissions are 10 times higher. So we'll have to see what this actually is is all this true that like data throughput is now going to fall, or is it just a battle of big companies trying to best each other? We never know. But this is an example of protocol failure. What happens when you don't stick to the rules? I'll go on from standardization protocols to communication protocols, and I promise we'll be faster as we go through each one. So basically, how do devices talk to each other? And I want to bring up the example of chiplet interconnectivity because it's kind of a hot topic right now in the electronics world. I'll tell you what all that means. But before that, communications protocols basically are a formalized system of coordination between two pieces of electronics, or within the electronics itself. So you could have how parts of chips talk to each other. So there are like protocols for this, which is called the advanced microcontroller bus architecture. There are also newer ones that are evolving that are not so ARM centric. Although ARM did open source this, but now open cores and a newly evolving RISC-V tile link is all open communication protocols. And you have protocols about how the devices talk to the outside world. So like we spoke about the USB protocol. PCI Express was is still very common. Like this, you put your graphics cards into a PC on a PCI Express lane. And now we have chiplet interconnects. And now this is a hot topic because chips are just too big. Now we want to break chips apart into small pieces and hook them up together with wires, and hopefully get the same performance as the big chip would get. And then, of course, you have over-the-air protocols like 3G, 4G, and all of that stuff. So this is very wide. This doesn't even cover remotely all the protocols that could exist out there. But what this does is it establishes the grammar required for two machines to interact with each other in an acceptable fashion. And if protocols fail, then it's just mayhem. I mean, just communication will just fail, and that's the end of it. Now, the whole silicon disaggregation trend, or the ability to break up a big piece of silicon into smaller pieces of silicon and hook them up, is important because the maximum chip size you can make on a 12-inch wafer. So that's the whole wafer as well. It's like a big disk on which all the chips are made, and then you can cut them out. The wafer is 12 inches, but the biggest chip you can make on them is 858 square millimeters, which gives you around 65 chips in a wafer. These are the size of like some of the NVIDIA GPUs today. They're really big. And the problem with this is that if there is a defect on the wafer somewhere, you lose a whole chip. And if you lose one chip out of 60, that's a lot. Right? So the one way to overcome one of this, at least the yield problem, is to break up the big chip into smaller chips. Smaller chips will have better yield because the same defect will only destroy maybe 1 in 200 chips now. And if there are parts of the chip that can be implemented in an older technology that's cheaper, because in leading edge technology nodes are extremely expensive to build on. So when parts of the electronics don't need it, people use cheaper technologies, and then you mix and match different technologies and hook them up with wires and make a chiplets-based system. But the main concern here is how do the chiplets talk to each other, and what universal protocols are required to make sure that chiplets can communicate and that everybody follows the same standard or protocol, because otherwise you just can't mix and match stuff. It's like USB-A versus USB-C all over again. They're just not compatible and therefore useless. So the idea is something like this. The Open Compute project wants to have a marketplace that's like a chiplets that you can go and get chiplets from and then hook them up into a chip and build the chip out. The idea is that it's much like a motherboard. So in a motherboard, you could put a CPU, you could put the RAM, you could put your graphics card, hook them all up through PCI Express, because that was the communication standard that made all this happen. And then you had a working PC. Now, how can that same approach be applied to chips? You could take chips from different vendors, hook them up, and then now you have a chip that is much like a motherboard, but way, way smaller. So that's the idea, at least. We're not there yet, but that's the vision. That's where we want to get to. So there are a few protocols that are available for chiplet interconnectivity, and that is like there was PCIe for computers. There are a few competing protocols out there. One of them is the Universal Chiplet Interconnect Express, as UCIe. And then you've got one like CXL, which is Compute Express Link, but more towards memory-intensive AI applications. And then you have bunch of wires, which is by the Open Compute project, which is a lightweight option. So now I think the industry is still up in the air as to which protocol will prevail in the long run, because again you have this efficiency versus thoroughness trade-off. UCIe is more on the thoroughness side, but bunch of wires is more efficient because it gives you the bare minimum you need to get the chiplets up and running. You don't need all the bells and whistles that the UCIe interconnect standard gives you. So this is where things are still up in the air. Validation protocols, like how do we make sure that the chip we are designing or any piece of electronics we design either works or intends or will work or is working or will work in the future? How do we make that happen? I have a story of how Intel lost $475 million in this situation. So validation protocols for a chip look something like this. So you have a multi-million-dollar chip and you give it a stimulus via simulation, and then you have an expectation or a reference model of how the chip should behave, and you compare your simulation with the reference model and ask if it works or it doesn't work. And the chip has a near infinite number of states these days, and the pre-verification process is to simulate every possible scenario and ensure that the chip works. This is equivalent to brute forcing everything, because you're just going to go through all the states that are possible in your CPU and make sure that every part of the CPU is working. And this is a common approach that is still used, and there are big fleets of machines that go through massive test suites 24/7, 365, hoping to catch a mistake. But the problem is that as when you go to floating point numbers, it becomes a big problem. You will never complete all possible combinations in a lifetime. So that has consequences. So in 1993, Intel had an FDIV bug. So basically what that was is a giant publicity nightmare for Intel, because the first Intel Pentium was introduced, and there was this researcher whose name was Dr. Thomas Nicely, and he was working on prime numbers, and he found that division of one particular prime number, it was basically a 1 in a 9 billion number, was giving the wrong answer on an Intel Pentium compared to the 486 systems that were before it. And he tried it on 2-3 different Pentium processors, and they all gave the same wrong answer. So somehow this reached Intel, who looked at it and said, this doesn't even qualify as an errata because it's 1 in 9 billion, and it's not off by a factor of like 50%. No, it's like it was off in the 10th decimal place. It's like it doesn't affect most people. Maybe it affects a few scientific applications, but most people don't even need this kind of accuracy. They said it's not even a problem. So the mistake actually was there were 5 missing entries in a lookup table that was being used for division. And the thing is that Intel did find this bug in their testing process, but brushed it off. And when people said they wanted to get a new Pentium, they said, why don't you prove to us that you really need this kind of accuracy, and then we'll give it to you. But this caused a big media explosion and really bad publicity. There is a whole blog article by Ken Shirif on this that explains all of this in gory detail. It's a fantastic read. I highly recommend it. But what ended up happening because of this was Intel's $475 million letter, which essentially said, we're sorry, call us, because no microprocessor is ever perfect, and we'll exchange your microprocessor for a new one. So they basically had to it is a really big recall, and cost them close to $500 million nearly 30 years ago. So that's a lot of money. And so what it taught us, I guess, in this is that Eto Frontier can sometimes be asymptotic. You can never be thorough enough. even though the bug was found, or 1 in 9 billion seems small and the error seems small, there is no way to test every possible combination, call it done, and ship it. It just doesn't. It's not a possibility. So it was time for a new protocol. This is where the Eto frontier would move, and the kinds of things that happen that Eto frontier moves. So there was a birth of a new protocol called formal verification that came out of this. So this is the alternative to brute force verification, and it lies in a esoteric computer science concept from the 50s called automated reasoning. So the idea is that how do you make computers prove theorems? It's not just about calculations. It turns out that in late 1990s, Intel saw that automated reasoning could be applied to hardware. And so this kicked off an entire research project, and Intel wanted to make sure that this bug was never found again. And so this gave rise to the field of formal verification, which then Intel went on to implement across the company, and with 2-week training sessions at various expertise levels to make sure everybody was aware of this newly invented protocol. And even today, it is a very essential part of it. So I don't want to get into the details of formal verification. I've linked a Substack article down here, and that which really explains how nicely now the formal verification can move the Eto frontier, because now with formal verification, we can make sure that chips are a lot more thorough rather than just brute forcing it like we did earlier. Even in chip testing protocols, you've got different kinds of chip testing, because once you get the chip back, you've got to make sure it works, right? So again, you've got this efficiency and thoroughness trade-off, because at the lab bring up and functional testing, you got the chip. The first thing you're going to do is it even alive, and do the major functions on the chip work? And if they do, how well do they work? And does extended functionality work, like the peripheral, the bells and whistles and features of the chip? And maybe you test a few chips and make sure that it's true on multiple chips, and call it a day. That could be a functional testing of the chip. And then you have the automated production testing, which is you can't possibly measure every function on every chip that is ever shipped out. So you have a reduced set of metrics you test on every chip, and then you get functional yield. Basically, you see how many parts meet this reduced set of metrics in production testing, and then you sort them out. Intel is also famous for binning parts like this, which means their CPU lines, even though it's made on the same process technology, depending on their performance, can be classified as an Intel i9, an i7, or i5. And then they're sold with different SKUs all over the world at different price points. So the protocols for testing also widely vary, and it really depends on how and what the application is. So automated test would be more on the efficiencies, because we want to make sure that every chip is at least alive before it goes out. But then when you do the functional test and lab bring up, you want to be sure that all the functions work. So you do thoroughness right there. Then we have methodology protocols. And this is important because how do you go through a chip design? The workflow and EDA tooling is very critical for companies with large design teams. And digital chip design has a workflow that's well established. You have a specification and architecture, then you do the RTL design, verification, synthesis, layout, and then send it out to fab. But then between each stage, there is a gate, there's a sign-off, and this is an interface where information needs to be exchanged and sign-offs need to happen. So there are definite things that have to happen before this whole pipeline can happen for chip design. There are gates and rules that must be met. And even within the design process, chip design itself has various design kits, because the rules and protocols for each one are completely different. Like if you are designing the chip itself, you would use the process design kit. If you are going to make a chiplet, assemble chiplets, you would have used the chiplet design kit. So on, whether you're assembling a board, a package, and maybe in the future even we have AI design kits, because AI-enabled designs are becoming more and more popular these days in chip design. So each of them handles a very specific aspect of chip design, and it is very important that the rules in that small domain are followed entirely. And depending on the methodology, the protocol varies in various organizations too, because if you are looking at academia or research or startup, I mean, the idea is to move fast. The goal is to get the product out the door or a paper published. So you're obviously not going to go through automated testing just for a paper in an academic journal. So the goals are quite different. You have the chance of more chaos and failures because you trade off thoroughness for efficiency. But in big tech and government, the emphasis is on being right. So it naturally gives rise to the bureaucracy that we are used to in big companies. So you have this fundamental problem if from a big tech manager who goes to lead a small startup immediately starts putting red tape because he or she perceives a lack of rigor there, or a startup founder, when acquired by big tech, they go on to start another startup because they see bureaucracy there. They have this differing mindsets along this frontier. And it depends on the end product too. Like if you're iterating a product quickly, efficiency is important. You want to make sure the prototype works at least. It's not a one-off, but you don't have to test maybe 1 million of them. But as you iterate from a known design, you go to more thoroughness as you go to a high volume product. So even the methodology for testing and design, everything depends on the end use and the organization it is part of. Documentation protocols, I say, are basically communication protocols, but for humans. And I'll give you the example in this one of NASA's $125 million fireworks show in the outer reaches of our solar system. Basically, this is in 1999. It was the Mars Climate Orbiter, which after 10 months after launch, it just explodes in space. And the purpose of this orbiter was to study the Martian climate. But then closer analysis revealed that the different scientists working on this used different units for acceleration, which JPL used Newton second square and Lockheed Martin used pound second square. And therefore, this was a disaster. I call this a documentation protocol failure because at some point, somebody should have mentioned which units to use, and everybody should be stuck to that protocol. But it is an unfortunate consequence that 10 months out of after leaving Earth, it disappeared. So documentation protocols are a love-hate thing because it really depends on what you're doing documentation for. So I came up with this little XY 2x2 quadrant system where you have on the x-axis more rigorous on the right side and more informal on the left side, and more text-centric on the y-axis. Up and below you have the detail-centric. So depending on what you're doing, you will be somewhere in this one. Like the paper napkin and whiteboarding would be on the informal but detail-centric side, because nobody really writes sentences on paper napkins or whiteboard. So it's less like diagrams and maybe equations. But then you have research papers that are more on the rigorous side, which have a combination of maybe mostly text and math. But then you have something like version control, which is almost entirely code maybe, or schematics. There's very little text, but it's also fairly rigorous. On the far left corner is, I guess, PowerPoint, which is both informal and text-centric, and in generally useless. When it comes to generating code, protocols exist, of course, for writing Python code, because Guido van Rossum, who's Python's benevolent dictator for life, said code is written much more than is written. Code is read much more than it's written. Sorry. There are style guides for coding. So there's PEP 8, which is Python style guide. Then Google has its version of that, and then there are anti-protocols. I think do not write everything twice or waste everyone's time. So don't do that kind of code. Or don't write smelly comments, which means you're trying to mask poor code by explaining it away. And there are version control protocols too, like when do you check in, and how do you merge code, and how do you release production code, and what do you do when released code fails? How do you backpedal to the previous version? So there are protocols for that. And even in documentation, when you think about citations, of course, IEEE has a format for citations. But then it's still up in the air. How do you cite AI-generated content in publications? I think the American Psychological Association has the APA has a recommendation to reference it like this. It says OpenAI 2023 ChatGPT March 14th version large language model. I don't see too many other styles. Like, I don't think IEEE has one. I've tried looking, but I think that's something that's still evolving, honestly. This is another documentation protocol that I particularly appreciate, because in 2004, Bezos famously sent out an email saying everybody needs to write a four-page memo. I think it evolved to a 6-page one, explaining that this is the only way that you can make your idea this is the only way your idea can be well communicated, and this is also the only way that you will truly understand what is it that you are working on. So he did not like PowerPoint style presentations in Amazon, and I believe he still does not, but PowerPoint still dominates as the info sharing method in chip companies. I mean, we still make PowerPoints all the time. Maybe it's for a lack of a better method, I'm not sure, but it's pretty dominant. Then there are the unwritten dynamics of working in hardware engineering, which is not it's not in your onboarding manual. Of course, there's a code of conduct. They don't be mean and you don't use foul language. But other than that, there's a lot of unwritten stuff. In electronic design, secrecy is very, very prevalent, because the tools of the trade are basically worth billions of dollars to companies, and they are very careful to keep that information secret. And then when you go to design reviews, that's an entirely different ritual, where a whole room full of people across multiple time zones will do a many-to-one interaction to poke holes in your design. Then there's whole thing about tribal lore. I have an example I'll tell you about tribal lore. Then there are power dynamics, like among team members. How do you say that your boss is wrong, for example, or things like that? Or how do you make sure that everybody equally participates in a meeting? Then there are territorial domains, because there are organizations in a company, there are people who work on them, and there are things that they do and that you don't do, but you have to stick to your lane in that regard. And there is then just the CYA, which is, let's find ways to avoid blame or liability. These are unspoken, but they do exist, and anybody who's spent long enough in corporate worlds see these things all the time. And the thing is that the walled gardens of secrecy are actually important. And it's very important because even somebody like me who writes a Substack has to be careful not to divulge any company secrets. And we have an entire, in Qualcomm, we have an entire legal process for going through this, which I have gone through and have gotten approval for. But they make sure that you are in accordance with their policies on this. And the other thing is that in companies, there's a need to know basis on many fronts. The downside of working on a need to know basis is that you don't have access to all the information you need at the moment that you need it. And it's always usually walled off behind access control. But then I see also why this is important, because when this protocol is not followed and a few bad actors leak information, then it becomes pain for everybody. And so unfortunately, these protocols have been put into place for a good reason. Tribal protocols are just things that people do in electronic design, but nobody knows why. And a classic example is Intel's U-curve, which means it comes from Intel's fabs, where they say like, there's a particular process in manufacturing which is yielding really well, but then when they build a new factory, the yield drops, and it drops for quite a while until they figure out all the little quirks, and the yield comes back up and it looks like a U-curve. They tried everything they could possibly do, and they could never figure out why this happens. So they adopted the copy exactly policy. What this means is that Intel will copy exactly what is in Fab A to Fab B and Fab B to Fab C. They will copy everything from the piping, the brand of paint, the construction plans, the building materials, everything as much as they can. They do this, and the idea is that in general, the idea in electronic design, especially when you're dealing with large-scale electronic design, is incremental changes are better than radical redesign, because there are so many unknowns that when you change too many of them, they all break down. And there's nothing you can do about this. This is the nature of the business. So a lot of times, even in RF engineering, people just don't know why things are done this way, but because the previous product worked this way, you just adopt the same thing and move along. And corporate territories exist too. So the protocol exists that the organizational structures can be blurred, but that doesn't mean you overreach and cross boundaries without the proper protocol. So you might have to communicate with appropriate managers before you go up there. Otherwise, you'll be viewed as taking their bacon, and it's not going to be fun. And then there is this blame protocols where teams go closer to thoroughness failure at the expense of efficiency to make sure that their block is bulletproof, even if it means padding deliverable timelines. And this is why chip design can slow down sometimes. And chip design reviews are also not entirely nice, because I've actually heard this in a previous work environment, that we are here to be correct, not nice. So it's a high pressure, tight deadline, prone to a lot of burnouts. And there's a lot of cultural dynamics inside the chip design world. And because of the large number of meetings, there are a few players that dominate the conversations, and then you can start to see sometimes Dunning-Kruger effects taken, because the really insightful ones don't say enough, and then engineers say what the managers want to hear, especially if it's close to review time. There are things like this that are quite common across the industry. And then I've got a last couple of slides. I'm not going to go into too much detail here, but the ethical protocols of working, about choosing intellectual honesty, that you don't cherry pick information, don't make graphs that leave out whatever that you don't want to portray, and definitely don't hoard your own personal secrets and not share it with anybody thinking it's going to protect your job security. And always company IP protection is important, which is the reason I put up my disclaimer. And none of this information is anything proprietary anyway. So I'm following all the corporate protocols that have been set forth to me. And I also try to make sure that when working with people, there should be a protocol for mutual respect, mental health, and ability to mentor people and not hoard personal secrets. But these are not written down in training manuals anywhere, but these are somehow still expected of you. And finally, there is this whole world that we deal with in electronic design where, you can't sell chips in certain countries, and there's a lot of politics, and then there are sanctions, and then there are tariffs. It's exhausting, and it's like an ongoing thing. I think this could be an entire book on its own. So I just want to leave that with a little cartoon and conclude my talk here. Hopefully I haven't gone too much over time, but thank you for listening.
Thank you, Vikram. That was very interesting. Yeah, we are over, but I did have a question for you before we conclude things, which was the auctions that are done for radio frequency engineering and like the band. I was curious because it's kind of this inexhaustible resource. Like you're never going to run out of access to it, but at any one time you can only have so many people using the band. But it's not like a farm where you could totally deplete the soil or like reduce the carrying capacity. Have those auctions failed in any way in the past, in a like historic way?
I don't know if they have actually failed, but the reason they are kind of exhaustible, I would say, is because when a particular frequency band has been given and auctioned away, there is a certain bandwidth around that frequency. So let's say you have 900 megahertz, which is common GSM band, and then a channel in that band might be a 40 megahertz channel. So you have only those 40 megahertz to communicate in, and that's all you get. And there cannot be too many users in this 40 megahertz band, because then you have too much interference. Too many people are talking in your ear and you can't figure out who's saying what. So that's why telecom providers buy certain communication bands, and they communicate within those bands so as to not mess with other people. I don't know examples of where they have failed exactly, but that's a good question.
Yeah, I'd be curious. And because it seems like those bands will always exist and they're very reliable. So like even if it's limited, and that you can only communicate within a certain like 40 megahertz. If you get that auction next year and you win, it'll be available to you. Or are there issues with maintenance of like the underlying band?
No, if you win the auction, yeah, the band is yours, and if it's yours, you can use it the way you want. And there are companies do sell large blocks of their spectrum to other companies to use, and that has happened in the past, and that's a perfectly fine way to do it. It's just that when a block of spectrum has been auctioned off to someone else for a lot of money, you don't want somebody else to start communicating in your spectrum. That would cause problems.
Yeah, that makes sense. Well, that was a very, very cool talk. As somebody who studied the efficiency thoroughness trade-off a lot, that was like a nice entry point to me to this very complicated topic. Yeah, I encourage everybody that's listening to go subscribe to your newsletter, vixnewsletter.com, right?
Yes, thank you. Yeah, vixnewsletter.com.
And yeah, I'm sure we'll talk more on the Discord and elsewhere. I guess we've got one more question if you're game from the audience, and then we can close things out. Would spectrum allocation become obsolete if cognitive radio becomes more popular?
Yeah. So there are ways, papers that I have seen floating around that explain how people should dynamically share resources, and that auctions are inherently a flawed way of going about allocating spectrum, because this is a resource that could be distributed among everybody in a better way. So I'm not sure if it can go obsolete, because I don't think certain entities will allow us, cognitive radio dynamic spectrum allocation, because the military has its bands. They're not going to let you communicate on military frequency bands. So certain parts of the spectrum are always going to be allocated away. But I don't know if it's possible to get everybody on board. But yeah, if we could share the spectrum dynamically, that would be far more efficient.
I think we even have a short story that's kind of about that, but it's about identities and as a scarce resource in the future. But yeah, anyway, thank you for coming on and sharing all this with us. The recording will be up on YouTube, and we'll talk soon.
Awesome. Thank you for having me.
Bye. Thank you, everybody, for joining. This is part of our guest talk series. We're having more this summer focused on teachers and more. Upcoming, I think, is Corey Levinson, who studies climate protocols, and he'll be joining us to talk about the state of play, how things are going with carbon credits and all that sort of accounting. And then we'll move on to more pedagogical stuff. We should have a dean from California speaking with us soon. And yeah, we'll see you online. See you on the Discord. Join if you haven't. There's a link at the top of the chat. And see you soon.